Today we're going to be starting a new unit which will cover electrical circuits. The whole unit is going to cover chapters 22 and chapter 23. We're starting out in chapter 22, which is about just current and resistance. Today's topic is current, which is modeled as moving charge. Really, that's the only thing about current, or the current model that you need to know. That current is moving charge, which you may have already known. The charges that are moving are called charge carriers. Now, charge carriers don't actually always have to be electrons. I know that's what we discussed in the first unit, and that's what's commonly known is that electrons are moving and that makes current. But it's also possible for regular ions, like you learn about in chemistry from specific atoms. It's possible that whole ions are moving around. This happens in fluid solutions mostly, but it's possible for there to be charge carriers that are not specifically electrons. However, in this course, we will mostly limit our discussion to electrons as charge carriers. If current is moving charge, then there has to be something that causes a charge to move. And we learned about electric fields extensively last unit. Electric fields are one thing that can cause the charged particle to move, and those are, I guess you could say, represented by a potential difference. They create a potential difference, whatever. We usually don't use electric fields when we're talking about currents, but they are implied when we're talking about a potential difference because the potential difference is created by an electric field. So that's one of the things that can cause a current. Another thing is a magnetic field. We're going to be looking at those next unit, so no need to worry about them here, but they can create a current, like spinning magnets are used to generate electricity. And the particle's speed that it is moving to create the current is what is called the drift velocity. So that's the velocity of one specific particle. So when we're talking about circuits and current moving, the current is moving because of a potential difference. And we talked a lot about potential differences last unit, but I'm going to draw out a circuit here and we're going to see how it works. So we were looking at capacitors last unit in circuits. Really, that's the only thing that we did in circuits. And when we looked at a capacitor, we saw that there was some potential difference across the battery. I'm going to make this side high, this side low. And we saw that the capacitors would reach that same potential because the charge would spread out all throughout the conductor to be the same potential. Now we're going to be looking at some circuits here. We're just going to look at a regular circuit and we'll add a little resistor in there. Haven't really talked about resistors yet, but basically it's something that uses up the energy that is in the circuit. So what's going to happen is that electrons are going to start over here, or charge, not necessarily electrons, and we'll talk about how convention and current works in a few slides, but charge is going to start off on the high end, and it's going to flow around towards the low end as it goes. And you would think if this is all conducting, it should all reach the same potential. And what is happening is that the charge is spreading out over the conductor from somewhere with high potential to low potential, trying to reach equilibrium where everything is the same. But the battery, which is right here, keeps taking the charge from this side, the low side, and pushing it back around to the high side, which gives it more energy. So then it has to flow all the way around again, and it's just a cycle. And it's continuing on, and it's because the conductor is trying to reach what's called electrostatic equilibrium, where the potential everywhere is the same. But the battery, which creates the potential difference, won't allow that to happen because it just takes those charges from the low side, bumps them up to the high side, and they have to go all the way around again. And the battery uses internal chemical processes to do this, which you can learn about in chemistry. We're not going to go into those here, but you can just kind of take it for granted that the battery moves the particles from a low potential to a high potential. And then the circuit is just the charge falling from the high potential to the low potential and losing energy along the way. Why does the particle lose energy? Well, it's a fun thing called resistance. So when particles, because they are actual particles, are moving inside a medium, even a conductor, they are going to collide into other atoms, other electrons, other particles. And anytime they do that, they're going to slow down a little bit and give energy to whatever they collided with. This is like friction in kinematics. And the medium, the particles in the medium are going to slow the charged particles down. That kinetic energy transfers to thermal energy. So if we got a circuit, looks like this, we're going to have our standard lovely circuit with the particles flowing around. They go through this little resistor, flowing around. Inside every piece of that is other particles. And anytime an electron hits, or a charged particle hits another particle, it slows down and makes that other particle speed up. Now, particles speeding up is thermal energy. So it's going to make all of the atoms or molecules that are inside the conductor jiggle a little bit more, which gives them some heat. Resistors are designed so that the electrons or charged particles can't pass easily through them. They cause a lot of friction, a lot of jiggling, a lot of heat, which is pulling the energy from those electrons, which is kind of the point of the circuit. The point of the circus. Oh gosh. Okay, it's kind of the point of the circuit. So resistance is good on resistors like that. It's taking the energy from the electrons and converting it into something else. And now a lot of people have this weird misconception about circuits. And that's that whenever the current goes through the resistor or the component, like a light bulb, that the current is used up or it is lost. And that is a really bad misconception. Due to the conservation of charge, as current goes through a circuit, it can't be lost because it's like actual literal particles. You can't lose the particles. It's conservation of energy, conservation of charge. That would break all sorts of crazy rules. So you can't lose the electrons as they flow around the circuit, and the electrons can't lose their charge. So the current is conserved everywhere throughout the circuit. And let's look at that in an example with a light bulb. So here's going to be our circuit. Whoop, whoop. And instead of an actual resistor this time, I'm going to make a light bulb. Very crappily drawn, but that is A-okay. So what's happening is there's going to be little electrons moving around the circuit. And they're going to be moving speedy quick. Lots of energy. And then they get over here to the light bulb. And what happens isn't that the light bulb just sucks up some of the electrons, some of the current. That's not how it works. It takes some energy away from that current. And the electrons will come out on the other side. They're just not going to be quite as energetic. So the light bulb is going to steal the energy of the charged particles, but it definitely does not steal the charged particles themselves. They just come out of the other side at a lower potential with lower energy. So we've been talking about the flow of current and talking about electrons. And here's where we come to something that is a little bit odd. And that is the conventional flow of current. So the conventional flow of current is the flow of positive charge, which in a physical situation is not what's actually happening. Physically, the electrons are moving. But for convention's sake, someone decided at some point in time that we'll say current or positive current goes from high potential to low potential. So current would flow like this, but we know that electrons actually go from low to high potential like that. So conventional current, when we talk about it, is actually backwards from the flow of electrons, which is weird, but it does mean that current flows from high potential to low potential, so like downhill, which is kind of good. But for this whole class, we're going to be using convention, and everywhere else in the world uses convention, that current is the flow of positive charge. Even though that's backwards from the way the electrons are actually moving. It's a mind bender. Don't know why they did it that way, really. But it's what we got to do, so we're going to stick with it. And here we have the mathematical definition for charge. It is the amount of charge passing through a specific cross-section of a medium, so usually that's a wire, so the cross-section is a circle, in a time interval. And the way that's written mathematically is this: I, which stands for current. I know, an obvious variable there. I, which stands for current, equals delta Q, which is amount of charge. And you could see if we were talking about negative charge, the current would end up negative, which is backwards from convention. So it all works out. And delta T, which is time, the amount of time it takes for that current to pass. The units are going to be 1 amp, which is equal to 1 coulomb per second. So these are called amperes or amps, abbreviated as A, all understood to be coulombs divided by seconds. And that's all we've got for current today. Really short introduction, no homework over it. Just kind of the basic idea of what current is, a little bit about what resistance is, and we'll get into it in more depth tomorrow.